All right, so this is going to be the first lecture for Math 314, and this is going to be on Chapter 1, which is Logic and Proofs. So we're going to start with Section 1.1, which is Propositional Logic. Now your suggested exercises are going to either be 7, 11, and 13, and this is if you're using the 6th edition book, or if you're using the 7th edition book, it's actually the same. Probably most of you are using the 6th edition book, but in the notes I've got them listed for both 6th and 7th because we used to use the 7th edition book, so if you bought your book or borrowed your book from a friend, like an old copy, then it might be 7th edition. Okay, so a couple of things. I'm going to ask you, not every time, but I am going to ask you for this time to read the whole section. So I'm not going to ask you this for every section that we cover, but there are a few reasons I'm asking you to read the whole section. First off, it's the start of the semester, you're developing good study habits, or you're deciding how much time you're going to put into each class, whatever. If you can set aside time for this class and work that into your study schedule, even though the starting material isn't super difficult, it's going to pay off dividends in the long run. This material starts out deceptively easy and gets very hard for some people, especially because a lot of this material has been covered in other classes, but because this class serves so many different types of students, we've got to be really careful about covering it all. So that's reason one. Reason number two is that if you are not used to reading like academic English, it could be very difficult to read this. So I want you to learn to read and to interpret this sort of higher level English now rather than when you're struggling with the concepts, because hopefully these concepts are not too difficult, so you can puzzle through the language and start to interpret sort of more formal speech, more formal writing, with the easier content. If we get to the middle of the material for the second exam and you're like, oh man, I should start opening the book and reading sections, and you're like, wow, I don't know how to read this language, that's going to be an issue for you. So if you read this section now, it'll be just easy for you in the long run. Okay, second, I'm going to ask that you work through examples 7, 9, 13, and 15. Now, these up here are exercises. Exercises are at the end of the section. These are examples. Examples are in the reading. So, end of the section, and these are in the reading. So the exercises are not worked out for you. The examples are worked out for you. So this might be a little confusing at first, but hopefully this starts to make sense as the semester goes forward. So what do we want to cover in this section? Well, I'm going to define some things, and when I define something, I'm going to put it in a box. So figuratively and literally. So I'm going to say a proposition or statement is a declarative sentence that can be either true or false. But not both. Okay, so this last thing seems like a little bit of a non sequitur. We'll get to that. Then a compound proposition is a proposition made up of other propositions. All right, so we have a proposition, we have another proposition. There are ways to combine them together. So let's go back to this a declarative sentence that can be either true or false, but not both. First off, what's declarative mean? Declarative means I'm declaring something. A is B, or water is cold. Whatever it is, I'm declaring something, as opposed to a command sentence like hand me the guitar. That's not true or false. That's just I'm commanding you to do something. So a declarative sentence is declaring or stating something. It's also not a question. Is the tea warm? That's a question, not a declarative sentence. Okay, fine. So now, what is this but not both thing? Well, let's do a nasty example that we're going to avoid, but I'm just going to bring it up now. So, example. This sentence is false. Okay, this, in the language of our class, we're going to say this is not a proposition. Even though it's a declarative sentence, I'm going to say this is not a proposition because it cannot be declared true or false. Now, if that's not obvious, that's okay. But let's just pretend for a second. Let's pretend that I've declared this sentence true. So if I've declared this sentence true, that means what it says has to be true. But what it says is that it's false. So if I say that this sentence is true, then that means the sentence is false, which means it wasn't true to begin with. Okay, fine. So since a sentence can only be, since a declarative sentence can only be true or false, then let's just naively, let's just say, well, then the sentence must be false. Okay, and move on. But hold on, if this sentence is false, then it becomes true, because if it's false, that means the opposite of it is true. But look, it asserts that it is false. But if it is false, then we've just shown that it's true. So it also can't be defined as true, evaluated as true, so it's a problem. So we're just going to say that this is not a proposition, and this is, sort of for the purposes of this class. There are ways of dealing with such sentences. We're just going to go on ahead and leave those out and not worry about those for the purposes of this class. We're not going down a bunch of logical rabbit holes. Okay, so an example of a proposition would be like, the sky is blue. Now you can argue that the sky is not actually blue, it's heather gray or whatever, but you can evaluate the sentence as true or false, right? You can either say, yes, the sky is blue, I think that sentence is true, or you can say, no, the sky is not blue, I think that sentence is false. So this is a proposition. Okay, moving on. To get to compound prepositions, what we're going to do is propositions. What we're going to do is take other propositions and combine them, and we're going to combine them using these basic operations. So the basic operations are negation, also known as not, conjunction, also known as and, disjunction, also known as or, and then some funny things. We've got exclusive or, also known as XOR, and this, we're not going to do a whole bunch of this in the class, but you do need to be aware of it for other things moving forward. Then we've got implication, which you might think of as if, then. Okay, that got rougher than even I can handle. And then, of course, we've got double implication, which is if and only if. And we often abbreviate if and only if as IFF. So this IFF is if and only if. So these are the different forms of modifications we can make on our propositions. And what do? Well, negation is going to assert the opposite. And there are about infinity different symbols used for negation. we're going to use this symbol. So if I have P, I'm going to say not P. So I've got this little high, let's zoom in here. I've got this high, like, right-angled thingy. That's the notation that I'm going to use. But you might also see minus P, P with a bar over it, tilde P, etc. Okay, there are about a billion different ways to do negation, but for the purposes of this book, I'm going to try to stick to this one. And if you've learned negation, logical negation in another class, and you've got some different sort of pet notation, I can probably figure it out. So use whatever you're most comfortable with in homework, and I should be able to figure it out. Okay, so if I have a proposition and I negate the proposition, I'm just asserting the opposite. Not super complicated. Let's move on. Conjunction is assert both. So this got really ugly. Assert both. So I would write this as P and Q, and this is a caret, right? So this is like a capital A without the crossbar. You might also see P dot Q or just PQ, but again, this is the notation that I plan to use for this course. So I'm going to assert both. If I say P and Q are true, I'm saying P is Q, and I'm also saying Q is true. So disjunction is assert either one or the other, or both. So this is also called an inclusive or. So I'm just going to make a note here. This is also called an inclusive or. The big joke is, the logician has a baby, and the doctor, delivers the baby to the logician, and the logician's friend says, "So logician, you had a baby. Is it a boy or a girl?" And the logician says, "Yes, because it's either one or the other, or possibly both." So this disjunction means if I say, "Is this A or B?" I'm not saying it has to be one or the other. It could be both. Okay, so the logician had a child that happened to either be male or female or both. So how do we denote inclusive or? We're going to write P and then a little v with Q. Now again, you might see P plus Q, and this is awkward because sometimes people use P plus Q up here. Oh no. Okay, so if you're going to use P plus Q, I can probably figure it out, but I would prefer you stick to this P little VQ. Okay, those are some of the more common things. We're not going to use much exclusive or, but I do want to talk about it. So exclusive or is one or the other, but not both. Okay, so exclusive or is like you're like 7 years old and your mom says, we can watch a movie or go to the pool, but not both. So we can either watch a movie or go to the pool, but not both. We've got, it's a summer day, we've got time to do one or the other, but not both things. And I think the notation the book is going to use is P plus inside of a circle Q. I've also seen P triangle Q. But I think, like I said, I think I'm going to stick to this notation, but I'm probably just not going to do much with exclusive or other than remind you that it exists. I might put it on like one quiz or something. Okay, now, implication. I know this is written as if then, but it's logically going to be a little bit different than that. So an implication is true unless the first is true and the second is false. That's the only time that this thing evaluates to false. And we're going to write this as P right arrow Q, and this is very standard notation. So implications are always going to evaluate to true, except in the case that the first part's true and the second part's false. Moreover, these first few up here, these are symmetric, but this one is definitely not symmetric. So if I switch the order of P and Q here, or here, or here, I get the same logical expression. But if I switch the order of P and Q here, I don't. Okay, so P implies Q is not necessarily the same as Q implies P. And we'll get to that. We'll talk about that in a minute. But let's now move forward. So a double implication is true. Oopsie daisy. True if the first and second are the same. False otherwise. And we write this P left right arrow Q. And again, this is fairly standard notation. So the the bidirectional or double implication is exactly the opposite of of exclusive or. So this one is true as long as they're the same. This one's false if they're the same. This one's false if they're different. This one's true if they're different. Okay? And we'll also formalize that in a little bit. So let's just make a little table and summarize the truth and falsehoods that we've generated here. So I'm going to make what I call a truth table. And the way I'm going to do this is I'm going to take one input P, another input Q, and then I'm going to draw this double line. And then I'm going to make a bunch of outputs, but I want to give us every possible input. So if you've seen truth tables before, great. If you haven't, also great. The important thing is that when you're making a truth table, you have every possible combination of true and false. So you've got true, 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 false, false, true. I put false, true twice. I want to make false, false. So I want to have every possible combination of true and false here. The idea is that I'm looking at every possible input to these sort of logical functions. So let's first do negation, which is not P. So negation is not going to depend on Q. Not P, well, if P is true, then not P is going to be false. P is true, not P is going to be false. If P is false, then not P is going to be true. Again, P is false, not P is going to be true. This is kind of a weird column because I'm repeating each input twice here. But let's get on to conjunction, which was the first one we did, P and Q. Remember, P and Q is asserting that both P and Q are true. So it's true in the case that both P and Q are true, but it's going to be false otherwise. And why is that? Because in all of the other cases, at least one of P and Q is false. Now we'll do disjunction, that is P or Q. This is going to be true unless they're both false. Because in all of these three cases up here, I've got at least one of them is true. Right? And the conjunction is true. It's either assert that either one or the other or both are true. So one or the other or both are true. Right? So now following this, we have the exclusive or, which I said I'm not going to do a whole lot with, but let's evaluate exclusive or. So we said either one or the other, but not both. So in the cases where we've got one or the other, exclusive or evaluates to true, but in the case where we've got both of them true, that's going to be false. Both of them false, it's going to be false. Okay, our last two here, we've got P implies Q. Remember we said this is always true except in this case here. It's always true except for the case that the first one's true and the second one's false. Other than that, it's going to evaluate to true every time. Finally, the bidirectional, or the if and only if. This is true if they agree, and it's false if they disagree. And what you should notice is that this column and this column are exact opposites of each other. All right, last thing that I want to do in this lesson is I want to give you the names of some, so I said that when we had implication, there were some things that we could do. So P implies Q. If this is the original implication, I'm just going to write implication. P implies Q. If I reverse the order of P and Q, and I get Q implies P, this is called the converse. So you might hear me say, oh, blah, 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 but the converse doesn't necessarily hold. Okay, that's something that I might say in class. If I have not Q implies not P, so if I start with P implies Q, and then I go to not Q implies not P, that's what we call the contrapositive. Now the contrapositive is going to turn out to be what we call logically equivalent to the original thing. Now what logically equivalent means is whenever this thing is true, this thing is true, and whenever this thing is false, this thing is false. So they have the same truth value regardless of their inputs. That is not the case for the converse. It's also not the case for this other thing called the inverse, and I don't know of any time that we use the inverse. I just think they had every other combination. They felt like giving this a name. I don't really use the inverse. I don't know what they're talking about. The word inverse has so many meanings in mathematics. I don't really like this. But it's in the book, so I'm going to at least define it for you. And I will